Okay, so in this video we're going to explore how different components behave as we change the potential difference across them. And the way we're going to investigate that is we're going to see what happens to their resistance as we apply bigger potential differences across them or even negative potential differences across them. So this circuit we can see here is designed to investigate that. So we've got a variable resistor that should allow us to change the potential difference across this one and change the current going through it. We've got a voltmeter to measure the potential difference across this. It's just a piece of wire wrapped up, so it's basically just a resistor. We've got an ammeter here to measure the current going through this component here. And then that comes round to, this time we're using a power pack, but it's on the DC setting, so we're supplying what we call direct current. Now, to start with, I've got the biggest shunt available on here, and you can see I've plugged into the 5 amps. Because I don't know how big the current's going to be, so I'm going on the safest possible setting to start off with. So I just want to start off by quickly sketching a circuit diagram of what we've got set up, as it's not the easiest to tell just by looking at it. So what we've got, we've got a DC power supply, so that looks like this. So DC power supply, you just see 2 blobs like this. We don't have to draw anything else. So we've got that is going round into a rheostat or variable resistor. Then we actually have the component that we're interested in. So we're just using a piece of wire, so that's a resistor. That is then going into an ammeter. So this ammeter is in series, so it measures the current going through it. And we've got a voltmeter in parallel. So basically we can measure the potential difference across it, the current going through it, so we can calculate the resistance using R equals V over I. So that's going to be our approach. And what we're going to do is we're going to change this resistance here. So we're going to change this V, and we're going to see what happens to I, and then eventually what happens to this resistance. Okay, so let's actually start this experiment, and we can go about collecting some data. So let's slot that in and bring the camera a little bit closer in so we can see what's going on. So let's turn up nice and high. Okay, so if we look at our ammeter, we can see the current is about 1 amp on here. If I turn this all the way down to its lowest, we go to, so with the variable resistor on its lowest setting, the current you can see is 3.5. So I should probably turn the power pack down a little bit because I can already feel the heat being given off by the resistor. So what I'm going to do is I'm actually going to drop the current even below 1 amp, so our resistor's not getting too hot. And so there we go. So this is on about 0.2 amps. So now what I'm safe to do is change down to a shunt with a lower setting. So this is going to stop my resistor getting really hot, but we get a much more precise reading. So let's now slot that in. Now we've got the current nice and low. Okay, so that, if you see that on here, so that one pinged to the left, which means I've got my connections the wrong way around. It also had quite a big deflection, so let's turn that down. Okay, so we've now got a good setup to actually carry out our experiment. So what we're going to do is take some potential difference and some current readings using this circuit. Okay, so let's actually collect some data from the experiment. So we've got a potential difference on this setting of 0.44. So let's actually get a table. So I'm going to have 3 columns in my table. I'm going to have potential difference. I'm going to have current, which is going to be in milliamps. And then I'm going to work out what the resistance is in ohms. So my table just looks a little bit like this. So our first potential difference, that's now settled on 0.43. The current, we're looking at this. So this is plugged into 100. So we're reading on the top scale that goes up to 10. And 10 on the scale is 100 milliamps. So we need to multiply whatever the number is by 10. So that is, I'd say, 5. that's 5.5, I would say. Yeah, so 5.5, so that's 55 milliamps. So that's what's going to go into our table here. We're going to get 55 milliamps on our scale. Okay, so if we actually then calculate the resistance, so we got 0.43, that's the potential difference, divided by 55, divided by 1,000, because the current is in milliamps, so we have to convert that. So that gives us a resistance. Let's convert that into decimal. So I'm going to just write 7.8 in my table as my resistance. Okay, so let's crank up the resistance of this one. So now our potential difference, you can see, has dropped to 0.25. Our current, this is, I would say, 3.2 on the scale, so that's 32 milliamps. So if we then do the calculation, so 0.25 divided by 32 divided by 1,000, and that gives us, see, 7.8 again. Okay, let's do one final potential difference before we turn it negative, or the other way around. So potential difference is now, what's that, 0.16. Okay, and then our current, I reckon that's 2.3, so 23. And then we do our calculation, so nice quick, so 0.16 divided by 23 divided by 1,000. And that's going to be 7.0 once I've rounded that one there. So what you're seeing in here is the resistance is staying pretty much the same. There's a slight fluctuation here, but we're pretty much the same resistance. So what we're going to do is we're now going to apply a potential difference the other way. And the way we do that is by changing these two over here. So if I switch these around, okay, so you'll see the potential difference reading on here is now negative. All that means is we've applied the potential difference the other way, and the current on here is also now negative. Now, to give myself a bigger range, I'm actually going to switch these two round, but the current reading, the value, is still negative here. So we've got a potential difference of minus 0.14. This current on here, so let it settle. So that's 2.0 on the scale, so that's 20 milliamps. But remember, that's minus 20 because the current's going the other way. So we're going to do minus 0.14 divided by minus 20 divided by 1,000. And you can see it's come out as exactly 7. There. And I'm just going to do one more negative one. So let's just plonk it somewhere. Let's not be too worried about what it actually is. So our potential difference reading, that's flicking around. It seems to have settled on minus 0.25. Current, remember we have to turn this into a negative number. I would say that is 2.4 on the scale. So 24 minus 24 milliamps. So we're going to do minus 0.25 divided by minus 24 divided by 1,000. Gives us 10. Oh, hang on. I think I jumped the gun a little bit before letting my circuit settle down. So you see the potential difference. I've got a loose connection somewhere. This reading is really flickering around, so one of my connections is probably loose. Can I get that to settle down? There we go. So it's now settled on minus 0. See, the talking starts changing. Let's keep it the same, minus 0.25. This current is really flickering around quite a lot. Okay, so I don't think we're going to get a reading here because none of my things have become stable. So I think we're just going to bin it. So if we look at this, you can see for our resistor, it doesn't matter whether the potential difference is positive or negative, and it doesn't really matter how big the potential difference is. The resistance reading stays approximately the same. It's around this 7 8 kind of region. And that's what we expect for one of these type of components here. So we often refer to these as fixed resistors, simply because their resistance stays pretty much the same, regardless of the potential difference that we apply. Now, if we were to take this data and plot a graph, what we call an IV graph, and we call it IV because I is on our y-axis and V is on our x-axis, what it turns out to look like is this. So it turns out to be a straight line through the origin, which is an indicator of a directly proportional relationship. So for a fixed resistor, potential difference and current are directly proportional to one another. And what that means is that I divided by V is going to be a constant. Or we could have said V over I is a constant. It doesn't matter which way round, as long as we do one divided by the other. So this is how we describe a directly proportional graph. Y over x or x over y is a fixed value regardless of the point. And we notice that V over I is resistance. And what that means is this graph shows you resistance is constant. So this is the IV graph for a fixed resistor. And in the next video, I'm going to take a look at the IV graph for something which isn't a fixed resistor, and we'll see what that looks like, the one for a filament bulb.